Newton's laws. Let's share the slides. Can you please tell me if you're looking at, oh yeah, you're looking at the slides, right? So what you have in here is a whole bunch of information that in some cases you just have to go and skim through them, but in some cases you have to pay attention to, for example, the units of the force, what does it mean, right? What is a force, which is a vector, because it has magnitude and direction. How do we measure it, right? For example, you have there the distortion caused by a force using a scale or using spring, right? So we are going to be studying different forces. The main one that we are going to be introducing, I introduced already, was the force of gravity, the weight, right? The weight is the force of gravity acting on a body. So we first start with the definition of mass in chapter 1. We continue it in chapter 2 now with the idea of weight. So weight is basically your mass times gravity, okay? And it's measured in newtons, while the mass, as you know, is measured in kilograms, or well, the basic unit is grams, but in most of the cases, we're gonna be using kilograms. Now, the force of gravity is obvious. When we look around, we use those concepts to differentiate how a person walks here on Earth and how the astronauts were walking on the surface of the moon, right? Because the gravity is much less, it's 1/6 the gravity of the Earth, right? So let's remember that the weight of an object depends on two things: the amount of matter, the mass, and the gravitational pull. In this case, the gravity of the planet or moon, or in some cases, the star, right? When you get close to a star, you get a strong gravitational pull because of the enormous gravity, right? And then obviously the idea of black holes, neutron stars, and so on. Friction is another force that we should be very familiarized already, because you actually experiment it every day. When you walk, when you try to move things, right, you have a force of friction, which is the resistance to motion. You can also talk about friction for falling objects, right? If you throw an object up or down, right, there is a friction or an air resistance. In chapter 1, we neglected, right? For an ideal scenario, we neglect the idea of air resistance, right? Of air friction. However, now that we're going to be talking about masses, bodies on tables or on the floor, right? We have to understand the idea of the friction as a resistance relative to motion, okay? So remember, if you look at this picture here, we have friction due to a body on top of a table, right? And actually, for this, let's use a whiteboard for this. Okay. So the idea is that if you have a horizontal table or a floor, and you have a mass, we have to start getting into the idea of free body diagrams or forces diagrams. In this idea, we draw the force of gravity like this. This is the weight of the object, mg. All right? So, when you apply a force, we know that the object will move. However, in some cases, depending how massive the object is, and depending on the surface, the object may not move because there is a friction here. There is a strong friction between the mass and the body here. We call that little f or fr, just to label it as friction. All right? So the friction opposes the motion that you're trying to give. In a frictionless situation, we neglect friction. But to have a frictionless situation, it's way too ideal. We are going to be solving problems or just giving examples with no friction, but generally speaking, there is always a force of friction. And the force of friction can vary. If you have, for example, an inclined plane with some angle, the body will fall also due to gravity. But for now, let's just say that gravity is acting, right? There is a force, there is a component of gravity making it go like this. But because there is friction here, then there is a force of friction that is opposite. The motion should be going like this. But there is also friction there. Right? So that's how you draw it. How do you measure it? So to measure the force of friction, there is a whole idea of normal forces. So look at this picture here. I wanna, actually from here. From Newton's third law, we know that for every action there is an equal and opposite reaction. So the weight of the object is pushing towards the floor is also pushing towards the body with what we call the normal force. This is the normal. We call it normal because it's perpendicular to the surface. In that case, the normal will be not like this. The normal will be like this. So it depends on the geometry of the problem, how you're going to find that normal. Right? The normal is perpendicular to the surface. So then, is there an equation for friction? Because we have an equation if there is an acceleration, right? Newton's second law, so let's write it here. Right? Newton's first law was, and we're going to recall all that, but Newton's first law was basically the law of inertia, right? A body will keep in its state of motion unless an external force acts upon it. Newton's second law states that, so second law here, that the net force acting on a body is proportional to the acceleration. That means proportional there. The equation will be F, the net force, equals to mass times acceleration. So we know this. But that's not a equation for friction though. That will allow us to find the force given the acceleration of the body. The friction that comes in two types, static and kinetic. Right? So you can have a static and static and kinetic. For the static force, the static friction, sorry, we call it F sub S. That's equal to the normal times mu sub S. And for kinetic, we call it F sub K. And that's equal to the normal times mu sub K. So you're probably wondering, what's that mu? Mu is a particular property of a surface. So a surface normally has both mu s and mu k. And as you probably are guessing, static friction is the friction due to a body that is not moving. Kinetic is the friction due to a body that is already moving. All right. So we probably won't do a lot of problems on that, but I'll show you a couple of examples. The most interesting ones are the ones on inclined planes. Those are actually very interesting because that's when you have to use the geometry of the problem. So I always find them very interesting, they actually go to the point, and we can see them here, right? So we see Fg or mg is the gravitational force, the force of gravity, the weight. But as you can see here with the plane, right, it's basically what I did on the board. You have to break, or the weight is broken into components. So we are going to learn that. Well, I mean, we'll do one so you can see, because you have to use cosine and sine for this, all right? But I think it will be very interesting, all right? And in fact, if you have seen already published week 3 extra credit problems, all right? I saw that many people did week 1, so that's good. Try to do week 2 as well, the ones with kinematics, all right? What I think I want to give you as well, guys, is an equation sheet. It's always good to have one, all right? Okay, so what would you guys say about these questions? True or false? Every force that acts on anything has a specific direction associated with it. True or false? If the force is a vector, right? What do you think about this? Is true or false? Anybody?
I think it's true.
It's true. It's a vector, of course. Which of the following is not a unit of force?
Ounce?
What was that?
Ounce? No?
Ounce?
Yeah.
Yeah? Kilogram as well is not force, and tons. These should be which are not. The only one is Newton here. All right, so kilogram, ounce, and ton are not units of force. All right. The force of gravity acting on an object is called what? How do you call that?
Oh, I think this one. It's weight.
Weight. Exactly. So when this is an interesting one. The air exerts a force on a person standing in a strong wind. This type of force, friction, by the way, is example of what type of friction? Static or kinetic? What do you think? This one will be kinetic. Some people may say it's static because the person is standing, but regardless, when you guys are walking or standing, your body is moving. It doesn't matter how, right? You are walking, you can be standing, you still the air and your body are still moving. So that's why this will be an example of kinetic friction. All right, this will be a kinetic friction example there. All right, let's recall Newton's laws. Newton's first law says that an object will remain at rest or in uniform motion, meaning in a constant speed, unless a force acts upon it. An external force, not internal forces, okay? An external force, a force pushing or pulling or lifting. All right? So we've talked about that before. That's an example of external forces. Then we have here the example of friction as well. All right? And all of those are vectors, right? And remember, a force causes a change on direction as well. Because if there is so forget about an object moving, let's suppose with some velocity, right? And then you change the direction, like you see in that example there. Then that's because there's an acceleration. And if you remember, even though the object doesn't change speeds, there can be an acceleration when there is a change on direction. The best example is what? Centripetal force. In a centripetal force, guys, which is inherent for circular motion, there is an acceleration because the object is changing direction as it goes around the circle. This happens in the merry-go-round. This can happen in a case like the one you are seeing there. Satellites orbiting the planet, right? Unless, of course, as you see there, the stream breaks and then the object leaves with constant speed. Well, it will end up losing speed because of gravity and air resistance. But the implication is that a change of speed, a change of direction does give you an acceleration, a centripetal acceleration, which hence gives you a centripetal force. All right? So an implication of Newton's first law is that the net external force must act on a body to speed up, slow it down, or change the direction. So you can make the object move faster, slower, or change direction. Because each of these is an acceleration, right? The first law will tell you that a force is required to produce any acceleration. If no force is acting, or if the forces are in equilibrium, as we're going to show you in a board in a bit, then you know that the object is static, and then the object will remain at rest, or at uniform speed. That's very important, Let me give you the example I gave to AP Physics 1 last year, and it was a problem, theoretical problem, right? I asked them, what should be the force to lift a bucket of water from a well that weighs 5 newtons, with water included, to bring it up from the well at constant rate, at constant speed? Again, what should be the force that you should exert to a 5 Newton bucket with water to bring it up from the bottom of a well? What do you think is the answer? You want to bring the weight of 5 newtons up, but at constant speed, without any acceleration. What do you think? The force that you should exert is 5 newtons. Of course, in a different direction. 5 newtons goes down. It's the weight of the bucket and the water. 5 newtons will be enough to bring it up at constant rate, because the forces are in equilibrium. You have 5 newtons going up, 5 newtons going down. What's the net force? 0. And that should be the answer for this question. For an object to move with constant velocity, the net force on it must be 0. All right? How about that? That could be a question. Remember, guys, Tuesday next week, in a week from now, you have quiz number 2. All right? So that's important that you know this. All right, these concepts. Homework is already there. I know some of you have already finished it, so that's good. But there, okay? True or false? It is possible for the net force on an object to be 0, even if several forces are acting on it. What do you think? Is it true or false? That the net force on an object is 0, even though several forces are acting on it. Anybody?
False.
It's true. Look at the board. Let me show you what I did on the board. Where is it? Look at the first graph I made. There. I'm gonna say that this object wasn't moving. There was a force acting there. Right? This one. But there's also the friction. So there's other forces acting on it. The force of gravity and the normal force. There are 4 forces acting in there. And the object is not moving. The friction is the same as the force, but probably higher. And there's also weight and normal forces acting, right? So there are 4 forces, no motion. That one as well, right? I said that you can have a situation where the mass, even though it's in an inclined plane, is trying to fall, but if there's no friction, it will remain static. And there are 2 forces already acting there. All right? So it's true. Okay? It's true. The force that must act on a body moving along a circular path is called what? What's the force acting on a circular path? Anybody? It's centripetal, right?
Yeah, that one.
Centripetal force. All right, we need to review that, huh? Mass. So to talk about Newton's second law, we need to know the idea of mass, right? But this is an interesting concept. When I was doing my undergrad, in one of the textbooks, I believe this is the Tipler textbook actually, but also the professor told us that mass is yes, it's true that mass is the amount of matter. That concept is used in physics but also in chemistry. But what is the difference in the way we use mass in physics with the way they use it in chemistry? You are seeing it right now. Mass can also be defined as the measure of an object's resistance to acceleration. The more massive an object is, the less acceleration you will have with the same force, of course. Because force is proportional to the acceleration. That constant is a mass. But if you give more mass, the acceleration goes down. Right? In the equation F equals to ma, if m goes up, a goes down. All right. There you have an example, right? You have big masses, small ones, and then remember, we use the kilogram to measure masses, but that scale that you're seeing there right now is on a scale in newtons. We call that a dynamometer, right? Well, nowadays it should be called more like newtometer. A dynamometer is a device that we use in the lab to measure the weight of an object with very good accuracy, actually. These scales, Newton scales, depend on gravity. In a space where if you are far enough from a planet in an empty space where there is no gravity per se, the weight will be 0, even though there is mass. On the moon, 1.6 newtons. So we're talking about 1 kilogram there. It's a 1 kilogram mass. And on Earth, 9.8 newtons, because mg is equal to 9.8. Gravity on Earth is approximately 9.8 meters per second squared. So there you are. All right. One question, and I'm gonna do this on the board because this was what Galileo discovered with using 2 different masses from the top of the Tower of Pisa. I mean, some people believe it's an anecdote only, but it's still interesting to think about it. Newton also corroborated this with his Newton's laws. If an object has a larger mass than another object, so you have a piece of iron and a piece of feather. What can you say about when they fall? Will they reach the earth at the same time? Guys, let's forget about the feather and the iron, because that was the experiment that was done in Apollo 14 in the moon, and I will explain that as well. But what Galileo did is he took 2 different balls, different masses, and he released them from the Tower of Pisa, from the top of it. And he noticed that they will reach the ground at the same time. Does that make sense? Even though they have, one has a larger mass than the other? Or can you explain it? Huh? Can you explain why objects with different masses fall at the same time? Well, there is a very easy explanation for that. I want to use this guy, Newton's second law. When the astronauts went to the moon in Apollo 14, the third mission, Apollo 13 failed, one of them, I don't remember the name, he took a hammer and a feather. And in live television, right, he made the experiment, he corroborated the idea of Galileo. He released them, a feather, and they both fell at the same time. You know why? You're probably wondering how come it works on the moon and not on the Earth. It's because on the moon there is some, on the Earth there is something that there is not in the moon, and it's an atmosphere. Because of the lack of atmosphere, there is no air friction. So that's also an interesting point. Air friction does act in daily life. We can neglect it, but there are some instances where we cannot. Like, for example, in the case of the feather will never fall at the same time of a piece of iron because of the air resistance. But on the moon it works. And let's see how it works. It's because if you have one mass, I want to call this M1, and you have another mass here, M2, and you release them, remember that gravity is acting on both. Because they are on the air, you are releasing them on the air, right? There are two forces acting. Sorry, there is one force acting on each. M1G, M2G. So yes, the forces of gravity are different because their masses are different. So how come they fall at the same rate? They are accelerating towards the ground. According to Newton's second law, the force is equal to what? Mass times acceleration. So let's write here. The only force acting is this. So I can say M1 times gravity is equal to M1A. And here, M2 times gravity equals to M2A. Aha! Look what I can do. It cancels. So A2, A1. So the acceleration for this guy is gravity. And for this is also gravity. They are falling with the same rate, the rate of the acceleration of gravity, 9.8 meters per second squared. That's why. And we use, any questions? The thing is that thanks to all of those equations and concepts, we've been able, as I said last class, to launch rockets to the moon, to put satellites in orbit, right? To study the orbits of the planets around the sun, right? By knowing things like this, right? And they were discovered 300 years ago. Anyway. What's the answer for the question that you have in front of you? The mass of an object depends on where the object is. True or false?
False.
True.
False. The mass doesn't depend where it is. The weight,
yeah.
the weight depends where the object is located. All right, be careful. All right, Newton's second law, we've talked a lot about it, right? It's basically the idea of objects being accelerated by an external force, F equals to ma. So you have here that a force gives you one acceleration, 3 times the force, triples the acceleration by, right, the same constant, 3f equals to ma, then the acceleration will be 3 times larger than the first case. And this is where we start using the equations, right? They give you an airplane with 2,000 kilograms, is observed to be accelerating at 4 meters per second squared. What's the net force acting on it? Mass times acceleration, 8,000 newtons, right? That's an alternate statement, all right, for Newton's second law. That's very easy, right? How can we combine this with what we did before? Let me give you a situation. So, the best situation will be if you have an object that is accelerated, call it m, where the initial speed, initial velocity is 0 meters per second. It's a rest. All right. In 10 seconds, the object will achieve a velocity of 72 kilometers per hour. I'm gonna do a review with you guys today, combining the units a little bit. If the mass is equal to 1,500 kilograms, so it's like a car, right? Find the force acting on it. So find the required force. All right. So we have the equation there, right? The forces, right? The net force acting on a body is equal to mass times acceleration. Again, for this type of problems, guys, we are neglecting friction for now. All right. Actually, let me see something here. Yeah, we'll do friction a little bit so you can see how it's used, because there's not much. Yeah. Okay. Force equals to mass times acceleration. We have the mass, we just need acceleration. And for that, we need chapter 2. Chapter 2, remember, the equation that you should have is acceleration is V final minus V initial over change on time. But you're giving everything, 10 seconds. So this is the time, delta t, 10 seconds. Initially 0, final though. We have to be careful with the units because the units have to be all in meters and seconds. That's in kilometers per hour. So we have to change it. And if you remember, I gave you the way to change kilometers per hour to meters per second. So 72 kilometers per hour, right? To go into meters per second, you do 1 hour equals to 3,600 seconds, and 1 kilometer, 1 hour, and 1 kilometer is 1,000 meters. Hours, kilometers. That will give you 72 times 5 over 18, which is exactly 20 meters per second. So I have my the final. So the acceleration will be using this equation 20 minus 0 divided by 10 seconds. That will be 2 meters per second square. I have that. Now I do Newton's law, Newton's second law. The force, let's use the magnitude, equals to the mass times acceleration. That's 3,000 what? Newtons.